Hello. Now we will look at graphs of real-life changes, or graphs of situations that we could do experiments for or that would happen in the real world. And specifically, we're going to focus on the change in heights of water as objects fill up. So if we take this small box, this small rectangular box A, and this larger rectangular box B, and we imagine that we put these under a tap and we start filling them up. So there's a hole in them somewhere in the top that we're able to fill in water. And it flows at the same rate into both boxes. So there's the same amount of water going into A and the same amount of water are going into B per minute. If we think about what the height of the water would be, so how high is the water up in the box after a particular amount of time, that's the graphs that we have for A and B here. So the water flows in at a constant rate, same rate all the time, and it's the same amount of water going in per minute into both boxes. What can we tell about this? Well, we can see that the water rises, the height of the water rises much faster in A than it does in B. And this makes physical sense because B is much wider. The base of B is much wider. That means that we need an awful lot more water to raise the height of the water in B. It's a much bigger volume to fill. So what we'll be looking at in these situations is effectively how narrow our vessels are, how narrow the objects are. So let's have a look then at some questions. What happens after 2 minutes? Well, in this situation, the water from our time axis we can see keeps flowing for 4 minutes. But after 2 minutes in A, the water doesn't get any higher, but we know it's still flowing. So what's happened? Well, the box must be full. It can't go any higher because the height of the box must be totally covered. We've filled the box entirely after 2 minutes. So the box is full. And then how tall is the box A? Well, if the box is full when the height is 10 centimeters, that means that the box is 10 centimeters tall, because the water can't go any higher than the box is, just overflows. Now let's have a look at drawing some of these sketches here. In this case, we were given numbers. We don't have to be given numbers. So in example C, in container C, we have the heights of the different parts of the container are given to us, but the amount of the water that's flowing in all of the time isn't given to us. So we can't actually draw a really accurate diagram. We couldn't plot points, but we can still describe what should happen in general. So what's going to happen in general as we fill up water into the container C? Well, it's got a very wide base, and for the first 40 centimeters of its height, it's this very, very wide container. But then after 40 centimeters, it narrows a huge amount. For the last 30 centimeters of its height, it's quite a narrow little pipe. So what would we be able to do? We would be able to draw in a line and say that the water is going to increase in height quite slowly. Because it's such a wide container, it's going to increase in height quite slowly for the first 40 centimeters. So up to 40 centimeters of height, where we have this wide thing, we have quite slow increase in the height of the water. But after that, we are going to be rising very quickly for the last 30 centimeters, which means up to 70 centimeters, we would be rising very quickly because the container is so much narrower. It takes a much smaller volume of water to raise the height. So that is roughly, as a crude sketch, that's what we would expect the height of the water to do in this type of container, where it's wide at the bottom and needs a lot of volume of water to raise the height, and then when it gets narrower, it abruptly starts to rise very quickly. So that's what we would have for C. Now for D, if we imagine this is an empty container to begin with, and we start pumping water into it at a constant flow rate, what's going to happen to it this time? Well, just like the wide base of this container, we start out with the cone that we've got here is quite wide, but it keeps getting narrower and narrower as we go up. So as we increase in height, the water height is going to rise faster and faster. So we start out rising quite slowly. But as time goes by and the water fills up and we're getting up more and more into the peak of the cone, where it's going to rise very, very quickly, we get this type of curve. I'm going to redraw that without the wobble. That's a bit better. So again, where the base of the cone is wide, the height is rising slowly. As time goes by, we're not gaining a huge amount in height because we're very wide at the base, just like we were for our container C. But as we go up higher in the cone and the water has, say, gotten up to this kind of level, we now have a much narrower object. So that means that it takes much less volume to raise up the height of the water in the cone as time goes by. So we expect that the height gain would be greater as time goes on. And then at this point, we would say that the container might be full. Now for a more complex shape like this, where we have a wide section and then a tapering section, this is very like a funnel. So what's going to happen up here as what's going to happen as we fill this up? So we have a closed container here and we're filling water in from the top. What's going to happen is that we are going to rise very quickly when we are down here because we have a narrow container. So we're going to rise very quickly because we have this narrow section here. But then once we get past this section, we start to get wider. So what's going to happen there? Well, as we go on, as time goes on, we're going to have a wider and wider section to fill, so the height is going to gain slower and slower. So it's going to taper off. And then when we get up to this section here, it's not going to get any slower anymore, but it's going to be going, it's going to increase quite slowly. So we have our three distinct sections. We rise very quickly, basically in a straight line, as we have a constant diameter for our funnel. And then when we start to get wider, we're going to slow down our height gain because we're getting wider and wider. And then when we hit our wide section that stays constant, we're back to a straight line in terms of our change, but it's now very gradual because this is such a wide container. And finally, what does it look like if we had water flowing out of something? Well, if we have this sphere, that's what this line is supposed to be. It's like the shine on a balloon or something like that. We have a 3D object here, or a sphere, and we have a hole in the bottom of it. It's full of water. What happens when we let the water flow out at a constant rate? So we still have water being pumped out of this at a constant rate. There's the same amount of water coming out every second. So this is not what would happen if you actually let a container pour water out of itself. It's out if you pump it out at a constant rate. What would that look like? Well, you'd start off with the water at the height of the container. So we'll say that this is the height of the water in the container. So it's that height there. We start out at that height. And then we're going to lose height. Well, we start off with it quite narrow near the top of the sphere, and then it's going to get wider and wider up to the middle, and then it's going to get narrower and narrower again. So we're going to start dropping height quite quickly. And then as we go down toward the middle point of the sphere, we're going to taper off, and this is around the middle of the sphere, where we're going to be going down quite slowly. It's a bit too flat. And then after the midpoint, we're going to start getting narrower and narrower again. So we start to drop the height faster and faster because we are getting narrower and narrower again, and then at this point the height is 0 because all of the water has flowed out of our sphere. So that is what we would expect for our water flowing in or out of our containers at a constant rate. And that's what we need for now.